Okay, students, let's get started on chapter 24 and talking about magnetism. Now, most all of you have probably at some point in your life had the opportunity to use a bar magnet or at least play with a compass. And of course, most everyone's cell phones, if you have a smartphone today, they have built-in compasses that you can use and look at. And what we notice is that we have what is called the north pole of the compass, or the north end of the compass needle. And of course, is there a south? Yes. But we typically orient ourselves with north. And so you've noticed that anytime you use the compass that it will always point north. It never points south. So this is very useful in navigation, and yes, navigators still use compasses. Okay, of course, most of them now are electronic, but there are times when they need to use an actual mechanical compass, one that's physical. Okay, of course, you should remember that like poles repel, just like charges, and unlike poles attract. Hence the reason the magnet or the compass needle points north. Well, the reason it's pointing north is because it's pointing towards south magnification. Okay. All right. Now, one thing about magnets and magnetism, you cannot create what is called a monopole magnet. All magnets are dipole. Okay, there's been experimentation to try to create a monopole magnet, but so far it has not been done. So if you take this magnet and cut it in half, guess what happens? You produce a north pole and a south pole now on two different pieces of magnet. Okay, so one thing you should always remember is that even though magnetic fields and electrical charges are similar, they are not the same. Okay, they are related, but they are not the same thing. Okay, one thing about magnetism is it is a long-range force. Okay, unlike the forces produced by electrical charges, they're very short range. Okay. Remember, the closer the charges are, the greater the force. The farther away, inverse square law takes effect. So magnetic fields work at greater distances. Okay. Again, we've already said that you cannot create a monopole magnet. That you always have dipole magnets. Okay. Now, one thing, of course, you've probably seen this in school, is that magnets produce magnetic fields. Now here we see they place charges in an electric field, and notice how they rotate and line up with the electric field. Okay, remember that protons move away and electrons move towards an electron. So electric dipoles produce a torque in electric field. Well, guess what? The torque, of course, and magnetic fields do much the same. Now, torque, of course, produced by an electric field tends to align with the dipole of the field. So the direction of the electric field is always the same as the direction of the dipole's axis. So the torque on the dipole is greater when the electric field is stronger. Okay, and that would go without saying. And of course, that would be proportional to the torque that is produced. Okay, same thing with magnetic fields. When you put a compass needle in a magnetic field, it will point always towards the north pole. Okay, it will point in the direction of the magnetic field. Okay, so if the magnetic field is this way, guess what? The north end of the compass will point in the same direction. Now, we should also remember, since magnetic fields have magnitude and direction, they are considered to be vectors. Okay, so yes, a magnetic field is a vector. Now, if you take here, we use this bar magnet, and we put the iron filings on the paper. And notice that we align the compasses around it, and notice how the compass needles behave. Notice here the south end of the compass points to the North Pole. Over here the north end points to the South Pole, and so forth, okay? But notice how in this location where it's parallel, notice that the compass needle is parallel. That's because the magnetic fields always travel from the North Poles to the South Pole, okay? And that's how the magnetic fields behave. Even the magnetic fields of the Earth behave the same way. Okay, now we can draw what are called field lines, just like we did with electric fields. Well, if you go back and look at that picture, you see that there's actual lines in there, okay? So we can actually represent magnetic fields by using what is called, or drawing what is called magnetic field lines. Now again, like I said earlier, notice how all the lines come out of the North Pole of the compass and move towards, or the bar magnet, and move towards the South Pole. Okay, and that will always be the same, okay? And so the South Pole of the Earth's magnet is located near but not exactly coincident with the North Geographic Pole, okay? And so when we look at this, we see then that the actual northern part of our world is south magnification, or south magnetism, excuse me, and the southern part of our world is north magnification, or north magnetized, okay? And that's why, and if you think about it, that makes sense, because that's why the north end of a compass points in the direction it does, okay? Opposites attract, okay? Now, they talk about here dip angle, and you can go back and read some more of this in your book. It's pretty interesting that as you move towards the poles, and if you're studying topographic maps, or if you're out using a topographic map to hike, if you're out hiking or trying to locate a particular object and get bearing and azimuth, you have to take this into consideration. It's called magnetic declination. Now, here around Boaz, Alabama, and here in the South, most places in the deep South, around the southern United States, don't have a large magnetic declination. I think here where we're at, it's about 1/2 degree of magnetic declination. We don't have that much what we call dip angle on our compass. But now if we go up to Wisconsin, or we go over to New York or Maine, we see a huge dip angle in the compass. Why? Because the south magnetic pole of the Earth is at a much greater distance away from the location that we are at, okay? And so we see places up in New York and Maine has a very strong magnetic declination, or dip angle, whereas places here in the South, it's very, very low, okay? And that's why. All right, so let's look at how we create currents. Of course, anytime you take a compass, we know that it reacts with a bar magnet, but what about electric current? Well, guess what? If you take an electric wire and you pass current through it and bring it near a compass, guess what? You will deflect this. And I'm trying to remember, I believe it's Oersted proved this, that a current passing through a wire will produce a magnetic field because it deflects a compass, okay? And so here we see this piece of wire has current flowing through it, and notice the orientation of the magnetic field, okay? Notice that. Notice how it's oriented. It's at a right angle, isn't it? All right. Now, so anytime, and notice it changes here when you have a loop of wire passing through a surface. Notice that the magnetic field is altered a little bit, okay, because it's a loop of wire. If you take several loops of wire, which is called a solenoid, you can see how the magnetic field arranges. Notice how it's very strong in the center of the solenoid, but once you get right outside the solenoid, it starts getting really weak really fast, okay? So the number of loops of wire and the length of the solenoid and the radius of the solenoid all come into play. Now, Mr. Shields, how do I know which way is the current going, which way is the magnetic field going, which way is the force, and we'll get to that here in a little bit. going, okay? Or if we're just looking at the velocity or the speed of the particle, you always take your right hand, always your right hand. And here they cup the fingers. Well, that's okay. You can cup them since it's a current carrying wire. But typically what we do, and you don't have to cup them, but you can, your thumb represents the direction of the current, and it also represents the velocity of the particle in the magnetic field. Your fingers represent the point in the direction of the magnetic field, and the palm of your hand points in the direction of the magnetic force produced. And we'll get to that a little later in the lecture, okay? So always remember that. It's a good little slide there. And so how do we represent that's on a piece of paper? If we're talking about magnetic fields, you have to have a three-dimensional representation. So if we're talking about the direction of the fields, then this is how we do it. We use crosses to say the vectors are into the page, and current. This is how we do current into the page. And if we do out of the page, then it's a little dot. Now that's vectors for the magnetic field, and that's the current, okay, out of the page, okay? And that's how we represent it. In other words, an X is into the page, and a dot is out of the page, okay? In other words, it's hitting you in the face, okay? And that's how we represent it if we're going to draw it. Okay, so what about loops of wire? Well, really and truly, the principles of the rules of the magnetic fields and how to determine them really don't change, because you're still dealing with current and magnetic fields, okay? So when we look at a current carrying wire, notice the direction of the current. In one place, it's here. Notice that here at this location, notice your current's this way. All right, the magnetic field, notice, is coming at us and hitting us in the face. Okay, well, and that would be the current. The current's going that way. The magnetic field actually is going that way, but since it's a wire, it wraps around. And then, of course, the force is also in the same direction. All right, now, so look right here. Notice if you come over here, right-hand rules, same thing still applies, okay? Remember, the thumb points in the direction of the current, the fingers, the field, magnetic field, and the palm of your hand would be the force, all right? Now, all right, so what about uniform magnetic fields? Well, solenoids are very good at producing uniform magnetic fields. And remember that the uniformity is within the solenoid, okay? So you can see how flat the field lines are. Notice how that it's basically telling us that it's somewhat of a fairly stable uniform magnetic field. However, once you get outside the solenoid, notice how the magnetic field really drops off and drops off fast. So what is this telling us? That when we go to calculate current or magnetic field using a current carrying wire, well, guess what? The current comes into play, but the radius comes into play. Now, so B, the magnetic field, and please write these equations down, depends on the actual strength of your current and also the radius of your wire. Now, since a wire is like a disc, shaped in a disc, or it's circular, we use, of course, 2 pi r. Now, okay, so notice this is for a current carrying wire, and notice we have this little constant here. Please write that down on your formula card, the permeability constant for magnetism, and notice it's mu naught. And it's 1.26 times 10 to the negative 6 Teslas meters per amp, okay? Now, the SI unit of magnetic field strength is the Tesla, okay? It is the Tesla. And so here is for a wire. This is the equation for a wire. This is how it would look like if we were to plot the current as we move away from the wire. Notice how the magnetic field really drops off, okay? Notice how it's strong close and weak far away. Okay, now, what about a current loop? Well, now this, you got to realize something, that the current here is coming up, hitting me in the face and going down there. In other words, we've got a loop of wire, all right? That's what we have. So how do we determine the magnetic field for a current loop, a loop of wire? All right, well, notice it changes just a little bit. It's no longer 2 pi, it's just 2, okay? So it's 2 times the radius. The radius, what? Of the coil, okay, of the loop of wire. Okay, and of course we measure that from the center. Now, very important, you write these down exactly the way we label them, because the equations are a little bit different. This is for a current loop. The other one, 2 pi r, was for a magnetic field in a wire. Now, what if you have multiple loops, such as a solenoid? Well, this is for N turns. Notice the only thing you do is put the number of turns in there, okay? Okay. All right, now, so what about solenoids? Well, again, notice instead of saying R, notice what it becomes. We factor that out, and it becomes the number of turns divided by the length of the solenoid, okay? So we can take the 2 out and just say, well, instead of it doing 2 times the radius, let's just say the length of the solenoid, okay? And basically, if we take 2 times the radius, that's basically what we wind up with, okay? Now, so we take the length of the solenoid divided into the magnetic constant times the number of turns times the current. Notice it becomes very simple. And this is for a solenoid, okay? Okay, for a solenoid, not the radius, but the length of the solenoid, okay? Very important, okay? And here they're showing you, of course, how to determine using the right-hand rule, the direction and everything, and it's just reviewing what we've already covered, okay? Now, what about magnetic fields produced by a charge, or charges placed in a magnetic field? Well, I've already told you this. Now, if you take, now look, if you'll take your right hand right now and lay it down flat and look at this diagram, notice that the magnetic field is in this direction. The velocity of the particle is in this direction. So which way should the force be? Okay, there's 2 possible forces they tell you here, up or down. All right, now if this is a proton, then it should be up, okay? However, if it's an electron, it'll be in the opposite direction, okay? Now, and it is a proton, so it has to be up, okay? But if it's an electron, it would be in the opposite direction, okay? Because the electron would be going that way, all right? And so you just flip everything over. But remember, this is right-hand rule now, and you literally use your right hand. So your thumb, this is your thumb right here. This is your fingers pointing in the direction. So that's the thumb, okay, right there. These are your fingers, okay, right here. And the force, remember now, the palm of your hand is pointing straight up, so that's the direction of the magnetic force, okay? Okay, and here they're showing you, now look, I don't like to separate the fingers. You can if you want to, doesn't matter. Again, magnetic field, velocity, that's the force, okay? You can do it that way too, okay? And there they're showing you that, all right? So it should be up, and I already told you that, okay? No duh. Now, that being the case then, so how do we determine the magnetic field force? And by the way, we should say F of B. That's how we should say it, because it's actually the force produced by the magnetic field. Well, notice we take the absolute value of the charge times the speed of the particle times the magnetic field and the sine of the angle between these 2 components, okay? These 2 particular properties, or I should say components. We'll say components. All right, fits better. So what do you mean? Well, if it's the sine of 90, if it's a 90-degree angle right here, well, the sine of 90 is 1. But what if it's a 45-degree angle? Well, then guess what? Then your force is going to be affected according to the sine of the angle, okay? So please remember this equation, and this is how we find the force, magnetic field force exerted on charges in a magnetic field, okay? So please write that equation down. Now, all right, what if the velocity of the particle and the magnetic field are perpendicular to each other? Well, if they're perpendicular, We don't need sine, okay, because the sine of 90 is 1. So notice the little simple change there in the formula. Now notice here, notice the direction of the field is going across the paper. The velocity of the particle is going to the left. Well, guess what? Then the force of the magnetic field should be downward, and it is, okay, using the right-hand rule. Okay? All right, now, okay, let's just move on. Okay. All right, so when we got charged particles moving in a magnetic field, and it's a uniform magnetic field, then we should have I can't talk. We should have a force that is proportional to that. And of course, if you remember when we found centripetal acceleration and centripetal force back in the last semester, notice that when we have a particle that's moving in a circle, okay, moving in a circular fashion, then we can find, and when it's moving in a magnetic field in a circular fashion, we can find the actual force that is produced using our centripetal force equation, okay? And you say, well, wait a minute, how will we know? Well, if we know the mass of the particle, we know the radius of the loop, then what we can do, if we want to find the velocity, we can use this right here and find the velocity of the particle. We can set these two equations equal to each other and solve for V or solve for R, okay? And it's real easy, okay? It's just a matter of algebra, okay? And so if I want to find then the radius of a circular orbit of a charged particle moving in a field, here we have a very simple equation. Notice what we did right here. Now look, all this is algebra, y'all. Notice what we did. We solved for R, and notice that this velocity squared canceled out. That velocity's gone, okay? Are you with me? And we wind up with this equation right here, okay? So if you want to write this equation down, you can. It's the radius of a charged particle moving in a circular orbit, okay? And of course, why is that important? Well, if you've ever wondered about the aurora borealis, they move in orbits around the Earth, and if you have wondered about how they form, well, it's from the solar wind ionizing the charges in the stratosphere and the and on up into the mesosphere and the thermosphere. Actually, it's in the ionosphere, the thermosphere, where it really gets supercharged and produces the aurora borealis and the aurora australis. All right, now what about force on a current? Of course, if you, and again, you should have already caught this, if the current is perpendicular to the force, the magnetic force, then we have maximum torque, we have maximum force. However, if the current is moving in the same direction, and notice here, now let me back up here again. Notice that the magnetic field is going into the page, the current is moving perpendicular to that, and notice that the force is perpendicular to the actual current, okay? Well, here again, you say, how do I do this? Take my hand, my right hand, stick my fingers down into the screen, my thumb is pointing in the direction of the current. Well, guess what? The force is in the same direction. Now, what if the magnetic field was moving in the same direction as the current? Well, guess what? You're not going to have any force produced, okay? Because the sine of 0 is 0. Okay, and there again the right-hand rule comes into play. So to find the force produced on a wire, all right, it's the sine of the angle times the magnetic field times the length of the wire times the current. And if it's at a 90-degree angle, we don't need all that. We can just find the magnetic force on a wire by multiplying the current times the length of the wire times the magnetic field, okay? I hope these diagrams and you see how they come into play. Now, what about current loop in a uniform electric field? Well, we produce something called a torque. And of course, in a uniform field, a dipole experiences torque, but there is no net force. In other words, it balances, okay? It exerts torque, but there's no net force. So how then do we find the actual torque? Well, to find the torque, Notice it's very similar to our force equation, magnetic force equation. Here we multiply the current. The only thing that changes here, instead of saying the length of the wire, that was length, right? Yeah, the length of the wire, instead of being concerned with the length of the wire, we look at the area of the actual loop, okay? And so the area of the loop times the current times the magnetic field times the sine of the angle between the two produces torque, or we can solve for the torque. Now they show you here how we determine this looking at your diagram. Notice you got the current coming up and hitting us in the face here and going down into the page there. So where will your torque be? Well, your torque is going to be perpendicular to that, okay? Maximum torque has to be perpendicular to that, okay? All right, and that's how we calculate the torque, and there was another equation. The torque depends, of course, on the properties of the current loop. Of course, I've already said this, the area and the current, all right? Now, when you multiply area times current, you have actually created another variable called the magnetic dipole moment, okay? The magnetic dipole moment, which I believe we use as U, okay? Magnetic dipole moment. Now, of course, the torque depends on the angle between the dipole moment, the current in the area, and the magnetic field. Remember, it's maximum when it's 90, but it is 0 when it is 0, okay? So maximum torque is when it's 90. When the magnetic moment's perpendicular, of course, the torque is 0, okay? All right, now wait a minute. Notice it says the torque is 0 when the magnetic moment is parallel to the field. And y'all, I said that a little bit earlier, okay? The torque is 0 when theta is actually 0 degrees, okay? All right, so when the angle, in other words, when the magnetic moment is parallel, when the current in the area is parallel to the magnetic field going in the same direction, y'all, there's no torque. But when they're perpendicular, then it is a maximum torque, okay? And I hope that helps.